Hello everyone, my name is Patron Tang, and I will be presenting the final project survey for system optimization methods. So my topic is network routing strategies. It's a topic which has been discussed by a lot of researchers. So let me start with the basic ideas of what is a network and routing problems. A network has expanded from solo traffic network to telephone network, electronic data network, transportation network, and etc. But in this presentation, we'll be mainly focused and talk about the traffic network. Routing problems are very common and applicable in real life, and this is the process of selecting the best path in networks. Maybe when you are using Google to try to find the shortest path from one place to another, that's actually a routing problem. And the references I studied in this presentation are as follows. The first is how bad is selfish routing. The second is selfish routing incapacitated networks. The third is achieving network optima using stackable routing strategies. So the organization for my presentation is like this. First, I'm going to tell you about the relations of these three references, and then I'll do some basic introduction about the network routing problems, and then we'll discuss the contributions for these three papers separately. And then we'll do some critical comparison, and hopefully we can provide some extensions or directions on this topic. So let me start with the relations of the references. I would say they are in the staircase type of relations for the three papers, because the first paper, selfish routing, tell us that it is actually very bad, and it tries to quantify how bad it is. The second paper tells us that selfish routing strategy is actually efficient enough in a more general case, but not restricted to the ones that were presented in the first paper. And the third paper tells us if we need to achieve this network optimum rather than the user optimum in selfish routing, we can use stackable strategies to form a regulated case. So the introductions for the network routing. What is routing problems and what are routing strategies? There are basically two types of routing strategies, non-cooperative and cooperative, as you may say. First, we have to decide a model for these problems. Consider the problem of routing traffic as in this presentation. We are given a directed network, and the rate of traffic between each pair of nodes. We need latency functions of each edge specifying the time needed or cost, and our objective is to minimize the sum of all travel times, which can be rephrased as the total latency. For the first type, which is non-cooperative network, the regulation is absent, so we use selfish routing strategies, and in this case, usually Nash equilibrium is used to characterize the operating points of such networks. And the second type with regulation or network management, we use maximum efficiency strategies. Because in this network, we have a manager who controls part of the network flow, and he's fully aware of the non-cooperative behavior of the users and performs his routing aiming at improving the overall system performance. So we have to induce an operating point that is efficient with respect to the performance of individual users as well as the system performance. This is called the Pareto efficiency. So let me start with the first type, which is the basics of the first two papers. So we first introduced the Brace's paradox. It's a very famous paradox which was brought by Professor Braces in 1968. It basically tells us the addition of an intuitively helpful link in a network can negatively impact the efficiency of a congested network. As you may see from these two pictures, the first one is a very simple network we can usually think of from the source to the destination. And we add one directed path between V and from V to W. And we may think that if the cost of this path is zero, it may actually be helpful for the system performance, actually which is not. We can calculate the agent latency for these two graphs. For the first one, it's easy to see that if we have the demand from S to T, let's say 1, so X and Lx should be 1/2 on each of these two paths. So the agent latency for each path, for each user is 1/2 plus 1, which is 3/2. But in the second case, if we are lured by the path which has zero cost, we may actually choose X to be 1. So the demand 1 goes from S to V to W and to T. In this case, the agent latency is 2, which is not as efficient as the first one. So, given this paradox, we usually try to quantify the difference between the optimal solution and the equilibrium. Actually, we can reach some kind of equilibrium in the second case, but it's usually not the best solution we can have for a total system. So the difference, if we want to calculate the difference, we must first give the math model. We give a directed network G with vertex and edge set. K is the source destination node pairs, and each of them is assigned with the positive rate Ri. And we have the set of simple ST paths with each path. And F is denoted as flow, which is a function. For a fixed flow, Fe should meet this following condition. And the flow is said to be feasible for all I if it meets this condition, which means that on all paths, the sum of the flow should be equal to the positive rate Ri. And each edge we assign a load dependent latency function, denoted by Le. And we have to assume Le is non-negative and differentiable and non-decreasing, because this is the first this is how we defined the model in the first place. It's a simple yet efficient model that we can discuss research into. So please note that the latency of a path P with respect to a flow P should be denoted like this, and the cost function to be minimized should be the sum of all the latency functions multiplied by the flow. So after given this math model, we can calculate the flows at a Nash equilibrium and also the system optimum. If a flow F is feasible for the instance GRL, it's called at Nash equilibrium only if and only if every I amount from 1 to K and P1, P2, which belongs to Pi, meets the following condition, which is Fpi is greater than 0, Lpi of F should be less or equal to Lp of 2 of F. If F is a flow at a Nash equilibrium, and F assigns a positive amount of flow, but they have equal latency, we should call the equal latency capital Li of F. Please note that each agent chooses only one single path in this network, rather than a probabilities distribution over pure strategies, or it should change. That's not how this is going to work. It's a different situation. So the flows at the system optimum can be derived to an optimization problem like this. So our objective is to find the minimum of the total cost of all Fs, but it's also subject to these conditions that the F is limited to a rate, and F should be each F on the E should be the sum of each path, F of each path, and Fp should be non-negative. So we can also rephrase CE, cost on each edge, in this form. It should also be the latency function multiplied by the flow function. The flow F is said to be optimal for a convex program in the above form, if and only if every I and P1, P2 meets the following conditions, which is Fpi is greater than 0, and the cost of pi at f of f should be less than the cost of p2 of f. So let's discuss more given the basic introduction in these network routing problems and try to find the contributions for the references. So as I mentioned before, the three studied papers come using at a staircase kind of relations in terms of topics, coverage of material and applicable conditions, and depth of knowledge. So let's start with the first one. The first paper is said to be the foundation or the basic for this kind of problem. It talks about the selfish routing, in which network users routes its traffic on its self-minimum latency path available. This paper also quantifies the degradation in network performance in such cases and proved that the performance is at most 4/3 times the minimum possible total latency as in the optimal for the network. But this is with restrictions. The restriction should be that the latency functions are only to be continuous and non-decreasing in the edge congestion. So if you want to calculate the difference from the optimal flow and the flow at a Nash equilibrium, we can first look at the Beckmann-Elliott corollary. The cost function of Li should be with margin cost is defined as this: Le optimal of Fe should be Le of Fe plus Le of Fe multiplied by Fe. So the only difference between an optimal flow and a flow at a Nash equilibrium is whether they accounts for or regards the second term. Which is denoted here. Then the flow of F is feasible for the instance GRL to be optimal. It means that it's at Nash equilibrium for the instance. And we also have to discuss about the existence of flows at Nash equilibrium. If it meets the condition that F and F to F prime are flows at Nash equilibrium, then their cost should be the same. So we need to discuss a little bit more about the upper bound or the upper bound in bacteria conditions. Suppose the instance and the constant R far, which is larger or equal to 1, satisfy the condition. We can denote rho to be a ratio of CF over C of F prime, F star, This means that it's clear that at the Nash equilibrium optimizes an object function, that it's at most R far away from the true objective function. It's noted as this: CF is equal to or less than R far of C of F star. And it's proved that the cost of a flow at Nash equilibrium is at most twice than the minimum latency flow. It can be also represented in a more general case where CF should be equal or less than 1 over gamma multiplied by C of F star. For F is feasible for the instance G, 1 over gamma R, and L. So the first paper proved the worst case ratio should be 4/3. So given the conditions that edges are continuous, non-decreasing, and linear, we may say LEX should be AEX plus BE, and the E should be lower notations, forgive me. So if A and B are larger or equal to 0, it's actually the same setting as the Brace's paradox. If we prove the theorem, we need to see that rho is equal to or less than 4/3. As you can see in this following simple way, by finding the lower bound for C of F over 2, we can easily prove that CF star is larger or equal to 3/4 C of F. So we get the ratio of 4/3. And then we need to discuss more about the contributions for the second paper. It also is talking about selfish routing, but it's actually an extension to the work in paper 1. And the extension should be, it gives the capacities to each of the edges in the network, congested networks. And it proved that the latency functions, if they are non-convex, non-differentiable, and even discontinuous, Nash equilibrium also holds in this condition, which can provide a very good system optimization optimum. So let me first introduce the Waldrop's principle of equilibrium so that we can talk about the later discussions. Waldrop has brought up these two principles in a very early time. The first principle is that the journey times in all roads actually used are equal and less than those who should be experienced by a single vehicle on any unused route. It means that the traffic flows that satisfies each user is usually referred to as user equilibrium flows, and because it only chooses the route that is at their best benefit. And the second principle is, at the equilibrium status, the average journey time is minimum. This implies that each user behaves cooperatively, although they are trying to find out the shortest path for their own. So, in this case, we can deem to be able to find the system optimum. So, in this paper, it provides a more simpler proof of the ratio 4/3. First, if we let X be a feasible flow, and we have the fact that equilibrium users travels on shortest paths of themselves, there we have cost of F should be less or equal to the cost of X. In this case, we can derive the following inequalities, where we can see that the first inequality holds because xe minus fe/2 to the square root of 2 is larger or equal to 0. And then combining these first two by this inequality and this inequality, we can easily see that 3/4 times C of F should be less or equal to C of X. Since X should be any feasible flow, we can choose X to be F star. So we have CF should be less or equal to 4/3 times C of F star. Then we introduce the capacities to the networks. So the link performance functions are typically nonlinear, positive, and strictly increasing with the flow. But a frequently used way to implicitly incorporate these capacities is to employ the volume delay formulas that tend to infinity as each edge flow approaches to the edge capacity. But in the user equilibrium case, the solutions usually doesn't comply with the Waldrop's first principle. So we need to extend the notion of UE. So we try to define this term as unsaturated if the cost on each edge is non-negative, and is denoted as CE. We have seen that with respect to a given feasible flow of F, FE should be less than CE, if and only if. Otherwise, it's called saturated. So it means that if F is larger than if the latency, if the flow is larger than the capacity of each edge, it should be called saturated. Otherwise, it's unsaturated. A flow of F represents a capacitated user equilibrium if no origin-destination pair, which is K, has an unsaturated path with strictly smaller cost than any path used for another pair. That is, for each path, its flow should be larger than 0, and for each path it belongs to the path set. The latency function of this path of F should be less than or equal to the minimum of this unsaturated latency. So for this UE, it has some different properties. The first is that it might result in the existence of multiple equilibria. In this case, it might cause inefficiency, non-uniqueness, and non-convexity of capacited UE. Take the first graph as an example. For these two pairs of arrows, we are supposed to move the demand from this point to this point, and similarly from this point to this point. Let's say each demand is 2 for these two pairs, for each of these two pairs. And the capacity for the common path shared by these two pairs is 2. And the cost is 1x, as denoted in the graph. So if we want to find the feasible flows for this situation, we must first see that if x equals to 1, we can easily choose W and V to be equal to 1. And V should be the flow from this point to this point, and W from this point to this point. If x equals to 1, W should be consistently equal to 1, and which is also equal to V. So we'll be having this line, which is W equal to 1 at the VW space. And also W plus V should be less than or equal to 2, as it's the capacity on this edge. So we have this line, and when V is larger than 1, we can see X is actually should be less than 1, so that it can happen. So along the thick
May I have
line.
your attention, please? We ask that you please keep your voices down as a courtesy to your fellow students. Thank you.
As the sorry, I was just interrupted. As we can see, the thick line denotes to the user equilibrium. So when V is larger than 1, and W plus V must equal to 2, because the common shared path is used at its full capacity. So in this case, actually we can see in the VW plane, the feasible flows are non-convex, and we have multiple equilibria which is along the thick line. So we introduced a different kind of equilibrium, which is called BMW equilibrium, when capacity is included to the user equilibrium. So if we include capacities as additional constraints to compute the user equilibrium, it's usually a common method we take. So the difference between the math model from BMW equilibrium is actually only adds this term, which we have each of the capacity for each flow, for each of the sum of flow on each edge, and the other conditions remain the same. So for the third paper, it states that the control decisions in non-cooperative networks are generically inefficient, as we can always see that if it's self-shooting, you will always be having a difference from the optimal solution as 1/3, according to the ratio 4/3. So in this paper, it devises a methodology for overcoming this deficiency through the intervention of a network manager. And by using the Stackelberg routing strategies, it derived necessary and sufficient conditions for the existence of the strategies we use in such cases, which is one kind of a maximally efficient strategy to achieve the network optimum. I don't think we have enough time to talk about this kind of problem, so hopefully we'll discuss this in the report papers. But the idea is that it's a complete different era from the ones we have already talked about selfish routing. So it may take a lot more time to discuss about. And if we are trying to do a critical comparison between these three papers, and we can see that the first two papers are both quantitatively talk about the selfish routing strategy, and it's based in the same model, same system. Paper 1 gives some more specific and detailed explanation of this problem, which laid the solid foundation for this problem, for this topic to be discussed in paper 2. So in paper 2, it actually explores the situation where the network is capacitated and when the latent functions are non-convex, non-differentiable, and even discontinuous. So actually the capacities is just one kind of the latency, one kind that the latency functions are non-convex, non-differentiable, or discontinuous. Thus, it's called a side constraint, sorry. So capacity is just one kind for the latency functions to be more general. In the third paper, it talked a lot about introducing the manager to achieve the system optimum for the routing problems, which is based in a completely different situation with the first two papers. So Nash equilibrium is generically very inefficient and exhibits some suboptimal network performance. There's like really the necessity to talk about the system optimum. So we need to use the Stackelberg strategy to achieve that goal. So that'll be all for my presentation. Thank you. If you have any questions, feel free to contact me.